welcome to gemchem. Now today's video is on alkenes part 5 video, and here we will deal with the last way of preparation of alkenes according to the methods which I have already discussed. Now Wittig reaction is the last one. So before starting, if you have not watched the previous videos on alkenes, you can watch it. I will give the link in the description box as well as the I button present above this video. Now let us start today's video. Now what is Wittig reaction? When primary or secondary alkyl halide is treated with triphenyl phosphine, we get a phosphonium salt via SN2. That is C. This is a alkyl halide. It can be primary or secondary. What is primary, what is secondary is already being discussed. So please watch the previous videos on organic chemistry, then you can understand. Now it is treated with triphenyl phosphine, that is this one, PPH3, right? So this is like this. It looks like P, a lone pair here, and 3 phenyl ring, that is the benzene ring here. Okay, now this 2 reacts via SN2 to form this one. This is known as phosphonium salt. Now see how the attack occurs. This lone pair attacks from the back side and forms this bond that is present here, and this X comes out. That is, this X can be any kind of halogens or any kind of leaving groups. Now we will see the next step. When this phosphonium salt is treated with strong base in suitable solvent, we get phosphorus elite. That is, when this one, that is this one, is being treated by base, what kind of base? It can be many types. Strong base is preferred, like PHLI in dry THF, or N-butyl lithium in dry ether, or NaH in DMSO, like this. So let us write the base, that is PHLI in the solvent dry THF. Similarly, N-butyl lithium in dry ether, and another option is sodium hydride in DMSO. So these can be used as bases, that is these which are present, and the bracketed part is the solvent. So this one, when reacting this base, what does this base? This base abstracts the proton present here. That is, this lone pair attacks this proton, and this proton is being grabbed by the base, and it leaves behind the negative charge in the carbon to form a ylide. Now see, this can undergo a resonance to form a double bond. No arrows should be shown while showing the resonance structures. It is against the rule. So we see that this negative charge comes here and this positive charge gets neutralized and we get a double bond. Next, this is the Wittig reaction. This ylide, that is this ylide, is treated with carbonyl compound and we get an alkene. See, this is the carbonyl compound and this is the alkene, right? So this is the carbonyl compound and we get an alkene, which is this one. This is the product, right? Now see what happens in the last step. We need to know the mechanism of the last step. Now see, this phosphorus ylide is also known as Wittig reagent, and it has certain stability. And what are the causes of the stability? Because there is 2 opposite charges in close proximity, and there is a vacant d orbital conjugation. D orbital conjugation is the reason for stability. Phosphorus has a d orbital and the lone pair gets conjugated. So this phosphorus ylide is known as Wittig reagent, and we see that there is a reverse reactivity or inversion polarity. That is, there is negative charge over carbon, okay, and positive charge over phosphorus. Now we will see the mechanism of last step, okay. Now see, this is our carbonyl, right? And this is our ylide. This is Wittig reagent. Okay. Now what happens? First, there will be carbon-carbon bond formation, and then there will be oxygen-phosphorus bond formation. Now, oxygen-phosphorus bond formation is very important, and whenever there is presence of oxygen and phosphorus, they will bond with each other rather than carbon-oxygen. Okay, and this phosphorus-oxygen bond formation causes the lowering of pi energy, that is pi orbitals energy, and the energy, bond energy of phosphorus and oxygen is very high. Okay, now first there will be carbon-carbon bond formation. Which carbon? This one and this one. So let us do the bond formation. Now see, this carbon, right? Then this and this one. Here oxygen minus and here PPH3 plus. Now see, this is known as beta-in intermediate. Beta-in intermediate. Okay. Now see, we can see that there is a negative charge and a positive charge. So they will try to neutralize each other. So what will be formed? There will be a oxygen and phosphorus bond formation, right? So the result is this one. Now what happens? There will be a transfer of bond. So carbon-oxygen bond breaks and carbon-phosphorus bonds also breaks. So the ultimate product comes to be as alkene plus phosphonium oxide. Now this has also another name, that is this one, this intermediate. It is known as oxaphosphatane intermediate. Oxaphosphatane intermediate. Okay. Now we will see how to prepare this one. Now carbonyl part is always taken to be the heavier one, always. Okay. Now so how to prepare it? First we will divide it, right? First there will be a division. So there will be two options, right? First there will be CH3Cl as alkyl halide and this one as ketone. Or another option is that it can be this one as alkyl halide to form the ylide, and this one, that is CH3, will become HCHO, right? Because we need two components, ketone or carbonyl compound and alkyl halide. So these are the two options. Now what I told is carbonyl part is taken to be the heavier one always. So what will be the result? Which one will be more favorable? Which one will occur more favorably? This one is bulky one, ketone part. So we prefer to have this option. Okay. So ultimately what will be the method to prepare this? This one will be the method. That is, this ketone is taken. We add CH3Br, PPH3. Now what this forms? This forms the ylide. Right. First step, number one step will result in formation of this one, CH3, PPH3 plus and Br minus, just like previous mechanism. Then on adding the base, that is second step, we will get this ylide. And this ylide will ultimately attack the carbonyl compound to give our desired product. So hope this was easy. Now we will go for next example. So first we separate, then we write the options. So which one is bulky? First we determine. Now see, this is containing pH. So this part is bulky. So we will have it as carbonyl compound. So PHCHO, and this part will be halide. So we will take it as any kind of halide. So let us see how it is prepared. See, this is the halide plus PPH3, then a base, and then PHCHO. So see, what will be the result of first step? We will observe it as this one. That is, this 4-membered ring P plus PH3, then Pr minus, then on adding the base, that is N-butyl lithium, we will get the ylide. That is, this part will contain minus and this part will contain plus. So we obtain the ylide, and this ylide attacks the carbonyl compound to give our desired product, that is this one. Right. Now this one is being prepared by this method, that is on adding further PHCHO. Now we will see for the next example. Now how this is prepared. Which part is bulky? We can guess this part is bulkier. So what will be our substrate? This one. So see, this will be the bromide part. We need to have cyclization. So there should be 2 ends occupied by bromide, so that cyclization can take place easily. And then we add 2 times 2 equivalents of base, so that for 2 times there is abstraction of 2 protons, right? So first, when we add this with the PPH3, then we get, see this one, we get this part, that is this Pr and PH3. This will be the product of the first step. Then we get, on adding 2 equivalents of PHLi, the ylide, that is PH3P plus and C minus, and this one. Right. Now on adding the ketone, that is PH2C double bond O, we get the product which we require. Right. Now we will see for the next part. Now stabilized Wittig reagent gives always trans alkene, that is the ylide with electron withdrawing group. Okay, then if it is electron withdrawing, the carbon has, we know that the ylide looks like this, right, with the carbon negative and a phosphorus positive. So see, if the carbon is negative and there is a electron withdrawing group present here, it will try to grab the electrons, so the ylide will be stabilized. So it will give result in transalkene. Similarly, if unstabilized Wittig reagent gives cis alkene, that is ylide with electron donating group. If suppose this is a electron donating group, then it will try to push the electrons towards the carbon. Carbon has already negative charge, so it will be destabilized, right? So more reactive means less stable. And the last one is, if the base is a lithium salt, then we get E alkene, basically transalkene, and for sodium and potassium salt it is Z alkene. Now see the example. For this one, see, this is a aldehyde and this is a ylide. Now see, this COOET group is a electron withdrawing group. So it results in the product which has a trans alkene, right? And for the next one, see this one, this group basically is a electron donating group. So it is a destabilized ylide, right? So it will result in a cis alkene. Okay, so it will result in a cis alkene. Next, we will see application. Now using Wittig reaction, we can convert a carbonyl compound into aldehyde with 1 carbon extra, that is CHCHO. See this one, this is a ketone. We know how to prepare this one. Previously we have already seen. Now on epoxidation, it gives this one. That is, there is a bonding with the oxygen. Then when BF3 is added, this epoxide opens up. And the O negative then gives up the electron to this carbon oxygen bond, and one hydrogen gets away. Okay, now this is a method. Another method is that if we add this ylide to generate this alkene, then on hydrolysis, that is adding H3O plus, we can get this product. So both ways same product but different method. So there is an application of Wittig reaction in both cases. This part is Wittig and this part is Wittig reaction, right? So this is one of the main applications of Wittig reaction. So this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.